Alright, so the first thing I want to do is verify that this does in fact match your drawing. So I've got a 5 amp heater, top connected to a 240 volt source here. The top of the source, or the top line connecting them, has a single pole thermostat drawn in between. Over here, I've got 240 volts between line 1 and line 2. Heater over here pulling 5 amps. This switch here is representing the thermostat. Top, just like yours. And I've drawn a fault. I drew it on the right side instead of the left, but it's a 1 amp fault ground. So you're suggesting that if we... Well, first off, let's talk about this fault here right now, okay? We got 120 volts there, we got 120 volts there, so we've got 240 volts across this heater. So this has got 240 volts across it, and is pulling 5 amps. Ohm's law is very, very clear on that. If we got 240 volts across something, and there's 5 amps going through it, then that means that this heater here is 48 ohms. There we go, 48 ohms. I can type it. Symbols that way. So your fault down here is between 120 and ground. 120 on one end, 0 on the other. The voltage across this is 120 volts. It's got 1 amp floating through it. 120 volts divided by 1 amp is 120 ohms. This is 120. Did I remember what code did that? Yes, I did. 120 ohms. Alright. So now, we're going to redraw your circuit as proposed. You want to put this fault on the other end. We'll do that. We'll do that. Alright, join those together. Alright, so now your fault is on the other end of the heater, right? So let's just run this with the thermostat off, alright? The thermostat is 100% definitely open. It's not even there anymore. I deleted it. So now what we have, since the thermostat is open, this part of the circuit right here is effectively irrelevant. Which means that I can take... Actually, we don't need this wire either. If we're going to do that, we can take this, draw it over here. Boink. Okay, so now I've got... This is effectively what we've got. The thermostat's gone, so we've got... And you just saw me. All I did was drag things around. I didn't change anything else. Your 120 volt line 2 hits this heater at 48 ohms. And then the fault at 120 ohms, where it is grounded. And of course, the ground, ground is ground. So these are definitely attached together, right? If those are definitely attached together, there's really no purpose to draw this. Yes, it is grounded, but it's irrelevant. The important part is there's a circuit there. Oh, this neutral down here. That was supposed to go with it, but Eagle's being a cunt today. Alright, the problem I have is, it's not really a problem, it's actually a good thing for me because it makes my point. If you go Google what the hell a voltage divider looks like, this is it. This is a voltage divider. So let's do some math here. How much current is floating through this? Well, the total is 120 plus 48 ohms, 168 ohms. You got 120 volts across it, divided by the 168 ohms is 714 milliamps are flowing through this. That heater's not going to get very hot, but 714 milliamps are flowing through this. Yeah, we'll just 714 milliamps is floating through that. And Ohm's law again. If we've got that many, I'm going to put that in the clipboard. If we've got that many milliamps, or that number of amps floating through 48 ohms, then the voltage across that 48 ohms is 34 volts. So in the example that you've given, your heater is at 34 volts. And just to verify that this all works out, we're going to take that number right there and figure out what the voltage across that 120 ohms must be. And that's 85 point whatever volts. So basically 85 volts here. So 85 volts. And again, I've rounded off, so it's not going to add up perfectly. But if I'm correct, because there's 120 volts across this total, 34 plus 85 is going to equal out to roughly 120, probably 119 because of the rounding errors. Look at that, 119. Now, A valid defense to this would be you arguing that the 5 amp and 1 amp numbers were only examples, and that there is a hypothetical situation where this would balance out and you get 120 volts across the heater. But let's look at that. In order to get 120 volts across this heater, there needs to be 120 volts total across this part of the circuit. The total voltage across the circuit is 120. In order for this right here to have 120 volts across it, that would mean, so if this here is going to have 120 volts across it, 120 volts, that would mean that this has the remainder, or 0 volts across it. Ohm's law again, if you have 0 volts across a resistor and there is current flowing through it, you can't do that. In order to have 0 volts across this, the resistance is 0 ohms. If this resistance is 0 ohms, then when we go all the way back here, because all we did is rearrange this, we go all the way back here, now this is 0 ohms, and if this is 0 ohms, then when this thermostat turns on, we are going to have a dead short, and we're going to have a trip circuit breaker. There we go. Beep. There is no situation at all where a parallel fault results in 120 volts across this heater. 4 volts, sure. 40 volts, whatever the math ends up working out to be with your exact heater, because this is not going, in a real-world situation, this is not going to be 48 ohms, and this is not going to be 120 ohms. But there isn't a situation mathematically where you get 120 volts across that heater, unless the only way, put that thermostat back there, the only way you get 120 volts across this heater is if this end is at 120, and this end is at 0, because that gives you a difference of 120. Any other number, any resistance here, any resistance right here, is going to cause the voltage here to go up, because you have a voltage divider through this, seriously? Through this, 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 and this. Plain and simple. It's a fucking voltage divider. Don't be retarded.